So welcome to the second workshop. Today we're gonna talk about the simulation passes in HFSS and the mesh refinement process. Then we will talk a little bit about basis functions. Then about what kind of computer requirements HFSS requires. And we will talk shortly about coil conductor modeling, what's the best way to model RF coils. And then a little bit, if we come to that, finite element method versus FTPD or RF coil simulation. Last time, if you remember, we simulated our first loop coil. And we plotted this magnetic field, and we saw that it's with the initial mesh setup, we get kind of a messy result. So, and the reason for that is we saw that when we looked at the mesh, that the mesh probably wasn't good enough. Can plot visibility. We can see that now. Yes. So this mesh, the initial mesh assignment is probably not good enough. But there's something like a mesh refinement process in HFSS, and for that I would like to point you to, which is also like very good HFSS help. Just like any other software, there's like a good help. So you can find it in the menu bar. And there, welcome to HFSS. Getting started. HFSS PDF. Yeah. So you have HFSS help, and then adaptive mesh refinement. You can search for it, and then you find a description of like how the mesh gets refined in the mesh refinement process. And HFSS does that in a way that he can find the software can find like a local error. So if you can see that, let's say in this region the error is pretty high, then he will refine a mesh there. But if you can see like in this region, you can see that the error is not that high, so he will keep the mesh size approximately the same. So the software is like very smart, and he can figure out locally a local error to the electromagnetic field, and according to that he will refine the mesh. So let's apply that to let's see what happens when we do that to our model. I'm going to open a new project, and I'm going to call it HFSS. I need to share those two with you, by the way. And copy this one into here, so we don't have to do the modeling again. And then in the analysis setup, which last time we set maximum number of passes 1. So now let's just run it to, let's say, 6 passes. And then we need to tell him when to stop. So because here we can see it's the maximum number of passes, but he can stop before. And the way we tell him to stop, we have like several opportunities, and the simplest one is to tell him the maximum delta S. And delta S is the reflection coefficient in the excitation port. So he can detect, or for every adaptation, or for every pass, for every mesh that he computes also the input reflection coefficient. And I'm going to see if it's selected. So for each given pass, he's going to compute the input reflection coefficient of the excitation port, and he's going to so for pass 1, he's going to compute input reflection coefficient. For the second pass, he's going to find a different input reflection coefficient, and then he computes the difference between the two. And if the difference is very small, that means that the mesh is good enough. But when the difference between the two is big, it means that he will try further to optimize the mesh. But it's always a question of of your model and of what you need, of the precision that you need. In our case, we don't care much about precision because it's just a single element. And yeah, I mean, this is only for the purpose of this workshop. But let's just put it to, let's say, 0.01. And we can see maybe later how that S parameter evolves. We can, in expression cage, maybe we can go into it later, but for now, I'm just going to tell you that if we put things here, he's going to show us at every mesh, at every adaptation stage of the mesh, he's going to keep the result, because otherwise he's going to keep the result only for the final stage. But if we tell him this parameter to add or to keep for every stage, then he's going to keep it for us. Actually, I want imaginary or none. Yeah. So hopefully now he will keep both imaginary and real part of the S parameter of the reflection coefficient. Okay. Let's double check. So we have excitation frequency is 3 Tesla. We didn't save this, so 6 number of passes, 0.01. So the first 2 tabs are the most important. Here the maximum number of passes, 6. And then we can tell him in the second tab minimum number of converged passes. What convergence means we will talk about later. And we can tell him here the order of basis functions, and that we will talk about later as well. But we can, for now, we can keep to 0th order, and just for comparison, let's compare 0th order and 1st order. Let's say we'll call this 0th order, and let's keep everything the same. And let's make this one 2nd order, just to compare what happens. Yeah, let's say 1st order. I need to rename this 1st order. Okay, so we have 2 models. One model, but with 2 different solution setups. The first solution setup is with 0th order basis function, and the second solution setup is with 1st order basis function. And we can just copy the models and paste them and just change one parameter, as you've seen, hopefully. And now I'm gonna, because I expect this to be a little bit computational intensive, or it might be, so I'm going to run it at a different machine, at a faster machine. So I'm going to save this again. Close. And I have a server machine that's much faster. And I connect it by VNC, and how to do that, we can also we can have another workshop on that, because this is kind of important as well for this particular software. Where did I set it to? Yeah. So again, before starting any model, we can say validate first, validation check, and it looks good for both of them, hopefully. Yeah. Now we can just say run analyze all, and he will run through the two models. So now we can wait for the results, and we can talk about them later and look at them later. So now the second point that I wanted to talk about is basis functions, which kind of we do like a hand-on experiment on those right now. We're comparing zeroth order and first order, and but we can also, meanwhile, we can look a little bit about the theory of basis functions. Be hung up. Well, he seems to be hung up, but let me tell you that basically these basis functions are kind of, oh yeah. Yeah, there's only text description, but describes the first order or tangential element basis function, interpolates field values from both model, blah, blah. First order tangential elements have 20 unknowns per tetrahedron. So in the first lesson, and now we looked at the mesh, and we saw that the numerical domain is discretized in tetrahedrons. And for the first order basis function, he uses 20 unknowns to develop the field. It's like if you think of polynomial functions, then yeah, basically the order of polynomial functions give you the number of unknowns. And here, because we have 3 dimensions and we developed some unknown in a tetrahedron, like a 3-dimensional unknown in tetrahedrons, yeah, for the first order, it has 20 unknowns, and 0th order 6 unknowns. So we expect 6th order to be much faster than first order in terms of computation. But on the other hand, first order is going to be much more precise because he can shape the field he's more free to shape the field. And then he can also do second order, which is 45 unknowns. And then you have also the possibility to choose mixed order basis functions, and then he will choose the basis function for each tetrahedron separately. But I guess that I'm not using that much because that may be slower for the software to choose the basis function. So yeah, this is just for you to know that, like, if you choose second order, it's going to be much slower but more precise. 0th order is going to be faster but less precise. If you just want to check a model or want to check just like a principle of something, then always choose 0th order if you don't care about the result that much. But if you really care about like the precision of, like, let's say for safety or for SNR assessment, then you could choose second order. You can also read more about this in like one dimension. And I think Wikipedia has a relatively good description on that. But yeah, I can send out links later. Yeah, so here he has like linear elements to describe to fit like a parabola. And yeah, if you extend it to second order, then he could fit not just linear elements but also like parabolic elements to it, and it would be much more precise. And I hope that's still clear. I don't want to go like very deep into theory because yeah, I'm not that proficient, and also it's not that important for us because we are more just using the software. But let's have a look at the simulation, and it looks like they both finished. So let me just here I'm on the server. So the server has the 512 gigabyte memory, and that's why it's much better for HFSS. Let me close it and open it locally. So now again, let's have a look at the quality of the result. Let me hide also the phantom. So you can right click on your model on the structure and say view hide in all views, and you can see that it's still messy, but it's better than it was before. This is the 0th order, and we can compare it to our previous result with only one. And let me add the mesh. So yeah, this was our first result with the initial mesh, and we were not happy with that. Now, of the 6 adaptive passes, we can see it looks a little better, but it's still relatively messy. And let's have a look how the first order looks like. Yeah, and it looks a little messy. I would expect like a symmetric solution, but it looks much better. Now let's have a look at the S parameters. How did they evolve during the solution process? And for that, let's have a look first at the 0th order, and we can right-click on results, and then say solution data. And here we can see on the second tab convergence. So we can see that he decided to, he stopped after the 4th pass, and that's because the abortion criterion that we gave him was fulfilled. So if we plot the maximum magnitude delta S, so that's the scattering parameter of the port of the difference of the scattering parameter between 2 adjacent passes. So we can see that it starts out big, but it goes smaller and smaller as expected because we refine the mesh. So the difference between is going to get smaller. And he brought it up after the 4th pass. yeah, so we can see that the mesh adaptation process works. Yeah, we were not happy with that solution, but we can if we increase the number of passes, the solution is going to get finer and finer, and it will even get more symmetric, and we can maybe meanwhile we can just let it run a little longer while we discuss the results that we just ran. So the first order one, let's let it run on the server again. Let's say just for example until 15 passes, and then we saw before the D aborted because he achieved the maximum delta S, and we can just say 0.001 or even like this, and we can tell him minimum number of converged passes 2. So he will make sure that he converged twice, because sometimes it can happen that the mesh will increase the difference again. Okay, let's save this. Close. And I'm gonna let it run on the server again, and we can yes, and we can also for the S parameters for each individual pass, we can plot the S parameter of that port, and for that we can say create module solution data report. We can say Smith chart for the S parameter, and then we can choose here between last adaptive, which is default, and usually he keeps only the results of the last adaptive pass. But we can also, because we told him to save the S parameter for each pass, we should be able to see how that evolved. So here these dots indicate the S parameter for each adaptive pass, and you can see if I go on with my mouse, then at the first pass the scattering parameter was here. At the second pass it was up here, fourth pass here, and third must be somewhere underneath. I can't see it right now. Maybe if I go closer, we can see that pass 3 and 4 are very close to each other. So we can see that the first pass was quite off with the initial mesh, and then he refined the mesh. And after the first refinement, the reflection coefficient jumped here. After third refinement here, fourth refinement here. So the difference is getting smaller and smaller. And the difference between the scattering parameters, he uses as an abortion criterion. You can set up different abortion criteria, but this is kind of the default one that he's using. And that's what we set here. This maximum delta S, we set 0.01. So when when the difference gets smaller than this, he aborts the adaptive mesh refinement, and he's finished. So yeah, either after 6 passes, or if he reaches, or if he's getting smaller than this difference. So that's what we saw when we right-click on results and solution data. And we can see the convergence here, and we can see that he aborted after the 4th pass. So now let's compare it to the first order basis function. Again, right click on results and solution data. And here he converged after 5 passes, which is a little strange to me because he should be more precise with the first order, but sometimes it's a little unpredictable with a mesh. So let's plot that, and here we can see different convergence behavior. He started out with a smaller difference, 0.01, compared to the 0th order. Here on the top, you can see the name of the model or the of the project. So this is the first order. He did flat first, and then he went down. He converged faster. And let's see how we can also see the mesh statistics. So for the first order basis function setup, he used about 7,000 tetrahedral meshes, and for the 0th order, he used 10,000. So we can see that for the 0th order, he needs more tetrahedrons to get to a similar precision. And this is also expected because the number of unknowns per tetrahedron are smaller. And we can also see, so we learned that for the same precision, we need more tetrahedrons for 0th order compared to first order. And let's see the memory requirement. So here we can see like the computation statistics for each pass. So he says adaptive pass number 1, and then we can see the memory requirements, and here we can see disk used 22.2 memory megabyte for the solver, which is here. Then for the adaptive pass 2, also 22. Adaptive pass 3, 21. Adaptive pass 42. Yeah, I guess he was the memory requirements are not big enough for him to see a difference. But let's have a look at the first order basis function. What kind of memory he used there, and we can see that he used for the solver 420. For the 5th pass, he used 420 megabytes, which is much higher memory requirement than for the 0th order. So sometimes, yeah, you are more precise with first order, but you also use more memory. So it's not always the best choice. Depending on the model, you have to make kind of your decision. Yeah. But yeah, if you go by default, if you use first order or second order, then you're gonna be definitely more precise. Let's have a look how our model is doing, and he completed already. And let's have a look at the solution data. So I let the same model run 15 for 15 passes, and let's have a look how the fields look like. Let me save it and open it locally because I run it on the server. So if you remember before, we were looking at the fields and we were not, the fields still look a little messy. This was after the 5th pass for the first order. And now we let the first order run until 15 passes. So the mesh is going to get even finer and finer. And let's have a look how the fields look like after 15 passes. Yeah, and you can see I may have to adjust the scale. Logarithmic scale. Yeah, and this looks pretty symmetric to me. Can still improve a little bit, but looks much better than this after 15 passes. And if you remember, after this after 5 passes, but to be fair, let's put it on a similar scale. Logarithmic. Oops. Or something is going wrong here. Yeah, I can't plot it in the logarithmic scale, but you can see that it's way more symmetric. And so yeah, so we can see that this adaptation process that the software is using works. And just for fun, we can have a look after 15 passes what the memory requirements were. So he did 81,000 tetrahedrons. If we look at the convergence, then we can see he can also like go up sometimes because it's not that predictable. But overall, he goes down, definitely. The difference between the S parameters between two neighboring passes will go down. And we went down to 0.001. And if we look at the memory requirements, we used 7 gigabyte memory to get to this result. So I could compute this locally on my machine. My machine has, I think, 32 gigabyte. I'm not sure, but if your model is getting more complex and if you need to run more adaptation passes, you can't do it like on a usual office PC. You need like a stronger machine, and currently we have like a server that is maintained by MCIT, and that has 512 gigabyte. So on that machine we can compute really like arrays or models that need more memory. So we talked about the simulation passes. We talked about basic functions. We saw that there is like 0th order, 1st order, 2nd order, and the higher the order, the more precise the solution is, but also the more memory we need for that. And why that is? That's because as we saw in the help, the number of unknowns per tetrahedron is getting higher. For 0th order, we saw there were only 6 unknowns, and for the 1st order, there were already 20 unknowns. And how finite element method works is it's matrix inversion, and so the matrix of that describes the model will just get larger, and the inversion will get more difficult. And for inversion of matrices, the thing that we need is RAM, or read-only memory. So for bigger models, we just need computers with higher, with more memory. Now it's almost getting 45 minutes, but we can quickly, I can show you how I would model or different ways of modeling Coil conductors. Let's just take first order. And I'm going to show you 3 ways of modeling Coil conductors. And we will just let this run, and maybe next time we can discuss the results. The first way of modeling Coil conductors is perfect electric conductor. And we have that already here. This was the first setup that we did. Let's just give it 20 passes just to make sure. First order basis function. Okay. Let's say minimum number of passes. Let's just let it run to 20 passes. It's the first way of modeling a Coil conductor. The second way is the second way is to assign it a finite conductivity. So again, we can select the sheet, right click, assign boundary, and then we should be able to see here finite conductivity. So he is applying he has some like mathematical model of how to treat this. When we assign him finite conductivity, I'm not exactly sure how, but he does it. And for perfect electric conductor, he makes sure that the tangential electric field on this sheet is 0. The finite conductivity, I'm not sure how he's exactly treating it. But we can also have a look at that. So again, we set 20 maximum number of passes, and we just let it run for 20 passes. And we can call it finite conductivity. This was perfect electric conductor, and this one we will, this is the preferred method. And in the preferred method, we can actually give the sheet a thickness according to the copper thickness that you have of your PCB. And then he has also different models of how he's treating it. I'm not exactly sure how he does it, but this is how usually the most precise way of doing it, but also it's going to take up more computational resources. So this we can right click on the let's visualize it. I'm going to hide the numerical domain, and we can again select the Coil conductor either in the model directly, or we can also select it in the model tree. Then say right click, edit, surface, and then we can say thicken sheet, and we can give it a thickness of 35 micrometer, which is the thickness of the PCB copper that we have in our lab. And then if we go closer, we can realize that if we go really close, we can see that he gave it a thickness. So, and then we need to tell him what kind of material the coil is, and it's copper. Okay. We did the model, and now we need to change the analysis setup again. Let's give it to 20 passes, and then the number of passes 20. Okay. And we can change the name. Second sheet. Let me save this. Yeah, so these are three ways to model the coil conductor.
Hey, yeah.
Yeah.
So with regards to, okay, so I got this point where you gave copper, but then like, don't you need to give it a conductivity? You don't, in the boundaries, doesn't it need to show a finite conductivity, or the way you did it is fine after thickening the sheet?
No, because I gave it a material of copper.
Okay. Oh, okay. So you define
the conductivity.
Okay, so okay, yeah, so I get it. Like, so, but like when I was doing it, I didn't thicken the sheet, but what I did was I gave finite conductivity as a boundary condition. But then in the finite conductivity, you can also go choose it. You can choose the material. Then I chose it as copper.
Yeah. So we have the comparison here, right?
Yeah.
So I gave it one of the models I did is finite conductivity.
Yeah, that's
conductivity is copper, right?
Yeah, that's copper conductivity, 68,000. Yeah, 68 million Siemens. Yeah.
Yeah, and so, but this is only a two-dimensional sheet. But here in this one, thickened sheet one is actually three-dimensional because I gave it a thickness, right?
Okay.
And here I don't have. It's the material.
Yeah, you don't have a boundary condition attached to it. It's just a material, right? Yeah. Okay. So okay, got it.
So in the model we see actually it's copper.
Yes.
It's the material.
Yeah.
So it's not exactly like he doesn't model it really, because he doesn't compute inside the copper.
Mm-hmm.
I think there's a checkbox like he doesn't solve it inside, so he still uses some like model how to treat this copper.
Okay.
But it's gonna be more precise, and next time we can see the difference between the two.
Okay.
So let's just let this run, and next time we can see whether there is a difference and like discuss what makes more sense. Okay, so that was the first part, I would say, and let's meet again at 3 o'clock. I'm gonna stop recording.